Away we go. Open it up. Follow along. If you guys are working on the questions and we're only halfway through the daggone lesson, listen. You should not be working on the 10 assignment questions, the ones you get a grade for, today. Shouldn't be doing it. We've got a couple of good simulations today. We've got reading to do. We've got review questions to do before you get to that. We will take the whole period, okay? So don't let me catch you on Go Guardian working on something else or watching a video or, okay? We got plenty to do before we get to that, all right? Pull it up. You should have a notebook out ready to take notes. The first three things you're going to take is going to be the first three laws, the three laws of planetary motion by Kepler, right? But if you're just sitting there writing and you're not paying attention, well, you're not entirely right either. I want you guys to try to pay attention. I'm going to read through this. Read along with me. First thing is we've got this picture of the solar system. I want you to tell me what is wrong with that picture of the solar system. What do you see wrong with that illustration of the solar system? What about the sun?
Everything. Too close.
Is it too close to the planets?
Yes.
The planets are too close to the sun? Does it look like they're like all grouped up on each other?
Yeah.
Yeah.
Right? Because it's an illustration. If it were reality and Mercury was that size, you wouldn't even see any of the other planets. They wouldn't be in this illustration. It can't be to scale if you're going to put it in that kind of a format. So
Yeah, but I can't. It's barely.
it's intentional, right? They have to do it that way. Are usually all the planets on one side, like in a straight line?
No.
Can that happen?
Yes.
Sure. Okay. But normally you wouldn't see it like that. The one I have on my back wall, where they're kind of scattered out around. I mean, I guess that's a little better, but still not to scale. Let's read. It tells us, hey, though a drawing, not an accurate portrayal of the solar system, the elliptical appearance of the orbits is right. Now, they're not perfectly right, because not all the planets have the same ellipse, or the same dimensions to the ellipse. But they're all elliptical. We knew that already, right? Remember just a few lessons ago, we talked about how orbits are elliptical. They're not perfect circles. The elliptical orbits around the sun are not limited to planets, comets, asteroids, other orbiting things also orbit in ellipses. Kepler's laws. 50 years before Newton and his laws of motion and universal gravity, Johannes Kepler published a number of astronomical papers with detailed descriptions of the motion of the planets. Included in those papers were the findings that we now refer to as Kepler's laws of planetary motion. When he wrote them, did he title them, hey, these are my laws of planetary motion? Do you think he titled it Kepler's laws of planetary motion? No. Why? Why didn't he? What do we remember about the scientific method? If you're going to call something a scientific law, and somebody just published their papers, or are just publishing their papers, their works, is it automatically going to be accepted as laws of science? No. What would they first be considered?
Theories.
Not even that yet. Not even theories. First they would be what? Hypotheses. So when he was publishing his findings, he would be publishing his hypotheses. Then they would have to be what? Yes, good. They'd have to be tested. And then if enough people are like, yeah, he's onto something here, and they start to agree on it, it can graduate up to what status? Theory. And then, I mean, literally we're a few centuries later, and we call it a law, because we haven't proved it wrong. It's still holding true. Okay? So here we go. The three summarized. Kepler's first law. Write this down. The path of each planet around the sun is an ellipse with the sun at one focus. One focus. There are two. check out this image. I love pictures because what's the expression? Picture's worth 1,000 words, right? So we have a short sentence describing Kepler's first law, and then we have a picture to help us understand, okay, we've got an orbiting object, and it's orbiting the sun, but because it's an oblong ellipse, there's actually two foci, aren't there? Two focuses. Plural for focus is foci, right? I think. So this little dot there is not an object. It's just a point in space. So the sun is a point in space, but it's also an object. It's the actual gravitational body. This is just ellipses have two foci, right? Okay. Though it seems at first glance that this law is incorrect, because the sun appears to be in the center of our orbit, remember that a perfect circle is an ellipse with foci in the same place. So if it were a perfect circle, obviously it'd be closed in here, but this second focus would be right on top of the other ones. They'd be perfectly aligned together, and that would make it a perfect circle. Since the Earth's orbit is nearly circular, the sun appears to stay in the center. All right, so to demonstrate that, you could draw, I'll do it over here. If you had this was the Earth's orbit, and here is the sun, the two foci, the two focuses would be like boom, boom, right there, very, very close to each other. Does that make sense? Because while our circle path is not perfectly circular, it's pretty close. Okay, moving on. Kepler's second law. Write this down. Second law. As a planet moves in its orbit, a line from the sun to the planet, you see there's several of them drawn here on the image, a line from the sun to the planet sweeps out equal areas in equal times. Because if the planet is closer to the sun over here, it's traveling faster. So in the same amount of time, it's going faster, but in the same amount of time, it would clear out the same area, two-dimensional area, as it would when it's further out and going more slowly. And if that doesn't make obvious sense to you right away, we've got a simulation that should help you understand it. The image above illustrates the relationship. Though the green wedges may appear significantly different in area, Kepler's second law states that the areas are equal if the planet travels along the perimeter of the segments in equal periods of time. From this, we can clearly see that the planet moves with greater speed when it is near the sun and slower when it's further away. I can demonstrate that with a beach ball, where the palm of my hand is the gravitational body that the planet's orbiting around. And as it bounces on it, the closer it gets to it, the faster it's going. So when it's just about to hit, and when it just hit, it's going the fastest. And when it's the furthest away, when it's at the peak or the apex or whatever you call it, it's going to be going the slowest, right? Fastest when it's by the hand, slowest when it's further away, just like an object orbiting another. Easy, right? Easy peasy. Yeah. Use the simulation below to observe a planet in orbit around a star. Start by adjusting the eccentricity, which is the measure of how elliptical its orbit is. So the more elliptical, the less perfectly round it is, the more eccentric it is. What do you notice as its eccentricity increases? Does it appear to speed up or slow down along its journey? Try to apply Kepler's first and second laws to make predictions about the planet's orbital motion before pressing play. So let's launch it. And it's going to tell us some things, and then we'll get started. All right, notice it's going slow
around the sun.
when it's furthest away, and as it gets closer, it starts to speed up.
Would it escape?
Zoom.
Does it speed up and slow down as it travels?
It does.
Why doesn't it just fall into the sun?
Because it has linear momentum.
Let's investigate the science behind this. Planets orbit the sun due to a mutual force of gravity. The force of gravity acting on the planet is anti-parallel to its position vector. This means the sun exerts no torque on the planet, and its angular momentum stays constant. A consequence of this is that the planet travels more quickly when near the sun than when far away. The total energy of the system is conserved.
So right here, we're going to see this again. Right here, the orange is total energy. That'll stay steady. As the planet is further away from the sun, it's going to have the most potential energy here in blue and the least kinetic energy because it's going the slowest. And when it's the closest to the object is orbiting, the sun, it's going to have the highest kinetic energy and the lowest potential energy, just like that beach ball that was bouncing on my hand.
Because the orbit is independent of the mass of the planet, we define the specific angular momentum and specific energy by dividing the relevant quantity by mass. Let's play around with different orbits in the sim.
All right, let's do that. So we're going to go to the sim. I'm going to give you a few minutes on your own. Let me just kind of demonstrate how it works, okay? Rothrock, you probably shouldn't be playing Drift Hunters. All right? So, in your notes, put this down in your notes, astronomical unit. They've got it here. I think they're just assuming we know what an AU is. If you didn't know what an astronomical unit is, it is a qualitative and quantitative at the same time value. Okay, it's a measurement, distance measurement. 1 AU is equal to the average Earth to Sun distance, which is about 150 million kilometers, or since we're Americans, 93 million miles. That is 1 AU. So distance from Earth to the sun, that is 1 AU. So on our sim here, when it says, hey, the semi-major axis is 2 AU, if we wanted this sim to be about the Earth and the sun, we would need to adjust this to what? If we wanted it to show the Earth to sun distance, we would adjust this to what? 1 AU, right? Okay. Here we go. Eccentricity. Earth to sun is pretty darn close to a perfect circle. Not a perfect circle, so we wouldn't have it at 0. We'd probably have it at 0.1. So you can see it's slightly off, just barely. In reality, it's probably closer to 0 than that, but that's okay. It's as close as we can get for the sim. And then the position angle just shows where it is in its orbit. So it doesn't really matter what you pick there. We're going to watch it orbit for just a second. Yay.
Yay.
Earth is orbiting the sun. That's now, good. Up here, if you go through each of these, each of them is going to give you different information. Okay, while you play the sim, it's going to show you different information. I really want you to look at this one, the show energetics. And then this first one actually does a really good job, especially if we increase the eccentricity to max. Check this out. I want you to look at this angle. Remember I told you the other day, we were talking about orbits, that it is a right angle. Do you remember I told you on average this is a right angle here? But look right now, it's actually obtuse, isn't it? Just like I told you. As I play it, you're going to see that angle go less than 90, more than 90. Less than 90, more than 90. Check it out. More than 90, 90, less than 90, 90, more than 90 as it goes around. But on average, it's a 90-degree angle. Okay, it doesn't matter what the eccentricity is, the average is going to be 90 degrees on the angle here. Okay, so I'm going to give you a couple minutes, play around with different settings, watch especially this one and the energy. Go ahead. Is everybody satisfied with that sim? If you want to play with it more, by all means go back to it. Okay, we're going to move on. Kepler's third law. Here we go. Kepler's third law. The ratio of the square. Guys, this we're just reading through this. It's going to sound complicated, okay? But I'm going to read through it, and then we're going to demonstrate it. The ratio of the squares of the periods of any two planets revolving around the sun is equal to the ratio of the cubes of their average distance from the sun. So what does that mean? T is time. They use the word periods, okay? So the period is the amount of time it takes to go around the sun. Does that make sense? So whatever orbital body is orbiting something else, the time it takes to make one revolution, that is the period, the orbital period. So that's capital T. T1 divided by T2, well, now we're comparing two different orbital bodies. So if we wanted to compare two planets, which we'll do here in just a moment, because the example one is Earth and Saturn, we would have T1 as Earth, and we'd have T2 as Saturn. And we could flip that if we wanted to. It wouldn't matter. It's a ratio. So that divided by that squared is equal to the radius, so the distance to the sun, of body 1 divided by body 2 cubed. They're equal. So if you take this value, it's going to be equal to this value. It's a statement. It's a mathematical fact. Okay? And it's the only of Kepler's 3 laws that deals with more than one planet at a time. This equation can be reworked, and this is the way we'll actually use it. You can rearrange the formula to make it more useful. So to reveal that the ratio between the period and the radius of the planet's orbit is always the same. And we can prove it, right? It says, in truth, it has been calculated that this ratio holds with all planets in our solar system, in addition to moons and other satellites. It doesn't matter what body is orbiting which gravitational mass. This governs how, this ratio governs how objects orbit other objects. Try to apply Kepler's 3rd law in the simulation below to help determine the right launch date to get a spacecraft to land on Mars. Then, because this law holds for all planets in our solar system, try other launches from Venus to the Earth, or from Mars to Venus, etc. I would suggest just trying to go from Earth to Mars, and then once you're successful there, try to go back to the Earth. But you can do whichever you prefer. You can watch me for a second, if you'd like. Just show you how to do the adjustments, and we got to listen to this guy anyway first.
If a spacecraft leaves Earth at just the right speed, it will enter an elliptical orbit about the Sun.
I tried it, mine didn't go.
If the launch date is calculated correctly, the spacecraft's trajectory will intersect the orbit of Mars. Now let's understand the science behind this. Kepler's first law states that the orbits of planets, and our spacecraft, are ellipses, with the Sun at one focus. We use the major and minor axis to describe the shape of the orbit. Kepler's second law states that an imaginary line connecting an orbiting body to the Sun sweeps out equal areas in equal times. Kepler's third law tells us that the greater the semi-major axis, the longer the orbital period. Let's see if we can plan a journey to Mars.
All right, here we go.
Why is mine always end up?
Huh?
Why? I tried it and my spacecraft kept getting lost.
Yeah, so you've got to time it just right. So check it out. For Earth to Mars, you're going to want Earth to be just like a quarter of a rotation behind Mars. And it'll take some tweaking, because this is really just trial by error here. But it's kind of fun. So you got to adjust your launch dates. So I'm going to try it here. You can see Earth is a little bit behind Mars. So if I hit play, the spacecraft launches, and it's going to try to catch up and intersect at the same time Mars is there. It's lost. Oops, it missed. So now what I need to do is adjust my launch. I'm going to try to get a little closer. This looks like it might be a little closer. Nope, still going to be behind. So play with that until you get it to catch it. Oh, this one's going to be close. Oh, it's going to be too far ahead. Oh, no. Slow down. Missed it. You can try to. Anyway, this is another one you can come back to try to get. And then, of course, down here you can switch your destination planet. So if we want to go to Venus, we can try to launch to Venus. There goes our spacecraft. Will Venus catch up to it? No, doesn't look like it. Spacecraft lost. All right, cool. So this is kind of fun. We'll come back to it. All right, example. The planet Venus has a mean distance from the sun of 108.2 times 10 to the 6 kilometers in a period of a little over half a year, right? 0.615 years. The planet Mars has an average mean distance from the sun of 227.9 times 10 to the 6 kilometers and a period of 1.88 years. Do these planets follow Kepler's third law? Get your calculator. Get your calculator. When I say get your calculator, I mean get your calculator. Believe it or not. I mean what I say, I say what I mean. And they do the first math for you, don't they? They actually do like all of it for you, but we can just confirm their math. So let's clear our calculators. And it says the average mean distance of Venus divided by the average mean distance of Mars. So we're using that first ratio they showed you. I have the more useful one there. But they're saying, hey, that's 0.475. And the period of Venus divided by the period of Mars is 0.327. Thus, you square the period and you cube the distance. Okay? So if we have the distance here, 0.475, and we cube it, we get 0.107. And it should be the same as when we square the period division between the two. So 0.327, if we square that, we get 0.1069, which rounds to the same. So the square of the period is equal to the cube of the distance, that ratio. So yes, to answer their question, do these planets follow Kepler's third law? Yes, because those two things are equal. Yes, what? When she's back. All right, so summary. Kepler's first law, second law, third law. Those need to be in your notes. If they're not already in your notes, please put them there. Review. We're going to do these three, and then I'm going to turn you loose. No, I won't either, because there's still more. There's still more. You're not going to work on any of that today. Why? There we go. All right. Can I erase this? Of course I can. If I can find my eraser. It's over there. All right. We're going to use, guys, in your notebook, do you need to close your computers? Do you need to close your computers to follow along? Probably. Go ahead and close your computer so you can follow along. Close your computer. Because I can't watch you on Go Guardian to make sure you're not playing whatever game y'all were playing. Okay? What was it? What was the game? Drift something? Yeah. All right, so we're going to use this formula right here. In your notes, put in the data, and I'll help you do it, okay? So it says the average mean distance of the Earth from the Sun is 149.6 times 10 to the 6 kilometers. And the period of the Earth is 1 year. We're going to call the Earth object 1. Is that fair? We'll have Saturn be object 2. So T1 is talking about Earth's orbital period, which is what? How long? How long does it take Earth to orbit the Sun once? It's a year. Yeah, 1 year. So 1 year squared, that's T1 from our formula. If we divide that by R1 cubed, and R1 is the distance of Earth to the Sun, we're given that right there, 149.6 times 10 to the 6. This, if you divide this by that, it will equal T2, which is the orbital period for Saturn, squared, divided by the distance of Saturn to the Sun cubed. So the difference of Saturn to the Sun is 1427 times 10 to the 6th. And that's cubed. It's an equation. We know it's true. This divided out is equal to this divided out. Do you guys remember ratios? When did you all first do ratios? Like 6th grade? I was told earlier, I don't know when you learned it, but I was told you learned it in 6th, 5th grade. Some of you maybe 5th. Ratios.
Oh, probably so.
So check it out. Correct me if I'm wrong, but don't we just divide down and multiply over to get this number? Check it out. Put it in your notes. We're going to divide down, and then we're going to multiply over, and then from that our answer will go up here. But because our answer will be this squared, we'll have to find the opposite of a square. What's the opposite of the square? Square root. So we'll put whatever number we get, we'll put it in the square root to actually find what goes in there. Does that make sense? That's kind of the plan here. So now there's 2 ways you can do this. I've got my calculator here. Earlier today somebody said, because I asked, because I didn't know. I said, couldn't we just disregard the times 10 to the 6th in these? Because you're dividing by 10 to the 6th and then you're multiplying by 10 to the 6th, so wouldn't it just kind of cancel out? And the person said, no, I think you got to leave that in there. So we're going to try it both ways and see if we get the same answer. Here we go. We're going to go, follow along with me on the calculator. Open parentheses, 1, because it's 1 year, close parentheses, squared, right? Divided by, close parentheses, or open parentheses, 149.6 times 10 caret 6, right? The little caret symbol for power of 6. And then close parentheses, caret 3, because the whole thing is cubed. And then we're going to hit enter. And you guys should have 2.986 blah, 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 times 10 to the negative 25th.
Yeah.
Right? Yeah?
What?
What? Is that what you got?
No.
Yes. No? Uh-oh. Okay, so should have been what you got. Now, take that times open parentheses 1427 times 10 caret 6 close parentheses caret 3 equals, and you should get what? 867.9, so we're going to round it to 868. You should get 868. Now, to find what actually goes here for the orbital period for Saturn, how long its orbital period is, 1 year essentially on Saturn is what? You're going to take square root, so second function of 868, close parentheses, equals how many years? 29.46, right? So our answer here is 29.46 years. That's Earth years. 29.46 Earth years is equal to 1 year on Saturn. Does that make sense? Okay. Now, but what I had said was I don't think we need to put in the times 10 to the 6th. Because if you divide by times 10 to the 6th, then you turn right around and multiply by 10 times 10 to the 6th, doesn't that just cancel it out? So let's try that and see how much easier it is to put it in your calculator. Because if we make things easier to put in our calculator, doesn't that reduce the risk of an error?
Yeah. Sure.
Yeah. So let's try that. We're going to do 1, because we can do that in our head, can't we? Isn't 1 times itself just 1?
Yeah. So
why don't we just say 1 divided by, go ahead and open parentheses, but all we have to put in there is 149.6, close parentheses, and then have cubed, so caret 3, enter.
Ooh.
Okay? And then we're going to go times, open parentheses, 1427, close parentheses, and then cube that, caret 3, equals, don't we get the same answer?
Yeah.
You guys see that? How much? You don't have to put that whole piece right here. you don't have to do that because you're dividing by it and then multiplying by it, so they just cancel out. Does that make sense? Okay. So sometimes you can see shortcuts in the math. If you see a shortcut, take it. Absolutely take it. Now you might want to double check just the process, but in the future now you'll know, oh, we don't have to put that in if it's the same. If this is the same as this, multiply, divide, it's gone. Okay? So that's number one. Number two, which of the following is one of Kepler's laws of planetary motion? Which one? A says planets move in elliptical orbits by the sun, with the sun at one focus. Didn't we just read that?
B.
Wasn't A the first of Kepler's planetary laws of motion?
Yeah.
Yeah. B, gravitational force between two objects decreases at the distance squared. What's that from? Last lesson. What was the last lesson?
The universal law.
Universal law of gravity from Newton, right? And C, an object in motion remains in motion. What's that from?
Third law.
Newton's first law, not the third. The first. Inertia, right? The law of inertia. And then D, inner planets orbit in different direction than outer ones? No. 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 All right. Number, guys, are you focusing? Number 3. If a planet's orbital speed is 20 kilometers per second when it's at its average distance from the sun, which is the most likely orbital speed when it's nearest the sun? When is it going faster? When it's nearer or farther from the sun? Nearer. Just like the beach volleyball getting closer to my hand if my hand were the sun, right? It's going to be going faster. So, what do you think? Is it going to be faster than the average or slower than the average? Faster than the average. There's only one answer that's faster than the average, so that must be the answer. What is it? D. 25 kilometers per second. All right, you guys still have a few minutes, but not enough. Okay. So here's what's going to happen. Yeah, it's some creepy looking teacher just like me, but just a different one. Guys, that's a 12-minute video. How about tomorrow we come to class, we watch the 12-minute video, we answer the 3, and then I turn you loose to do your 10 questions for credit. Okay? Sounds good. Nobody needs to be answering those questions today. All right? If you guys want to start working on this, you can, I guess. We only have a few minutes left, so we're good. You guys want to play map games?
What?